Hello, welcome to lesson 8.4, 5, and 6. We're going to talk today some more about bonding, and then we're going to move on into electron configurations. So when we talk about electron configurations, that actually kind of helps us determine how things bond, but we don't normally look at it that way. We look at the periodic table. And so if we look down here at the periodic table, and these are not in this particular periodic table is not in the notes that you printed off. I embedded it in this document to help explain things. So previous to this, we were naming compounds and things like that. We would say things like this column would be a +1, and this column would be a +2, and this column would be a -1, and so on. What that's actually doing is alluding to these electron configurations that we're going to talk about shortly. So the first little piece here that says generalizations that apply in stable compounds, that's really what that's talking about. When you have a covalent bond, what's happening is both of the nonmetals are trying to gain what we call a noble gas electron configuration. Same thing when we have an ionic bond, the nonmetal is going to add electrons to obtain that noble gas configuration. And then the metals are going to empty electrons so they can get that noble gas electron configuration. And so this will all make sense within the next lesson when we start talking about electron configurations. So ionic compounds, what ionic compounds are wanting to do is they are wanting to structure themselves, and they'll have what they call a lattice energy or a lattice structure that structures themselves so that there is the minimal amount of repulsions and the maximum amount of attractions. The part that talks here, predicting formulas of ionic compounds, that's what we did before. Only in this time they're using the electron configuration. So there's the electron configuration for calcium, there's the electron configuration for oxygen. So what will happen is these two electrons on the calcium will actually move over here and give this a full outer shell. So that will be a 2p6. And so its electron configuration will be like that of neon. So in talking about this, and it's like was said earlier when we learned about naming compounds and figuring out what the formulas for compounds would be. Metals in group 1 lose an electron, group 2 lose 2 electrons, group 3 lose 3, group 7 gains, group 6 also gains. And so what that goes back to is that this is going to be a +1, this one's going to be a +2, this one, at least aluminum in that column, is going to be a +3, -1, and -2. So that's what that's talking about, only it's using a different language to discuss that. Sometimes there'll be exceptions, and so like if you look here, this is 10, and 10 would be in the column that would be ±4. Because that's what the carbon is. But tin can form +2 and +4 ions. Bismuth should be a -3, but since bismuth lands on the left-hand side of that stair-step line, it won't gain electrons, it'll lose electrons because that's what metals do. Okay. So there are some exceptions to that, and you do have to watch for those. In determining whether or not a compound is stable, another determining factor is ion size, and how, obviously ion size is going to predict how things pack in together. So what influences ion size is the size of its parent atom and the position of the parent atom in the periodic table. So let's look at this, and I think it's best to look at this in terms of examples. There are such things as we call, before we get into the examples, there are such things as we call isoelectronic atoms. And isoelectronic atoms mean it has the same electron configuration. So electron configuration, if this will write, electron configuration is the same in isoelectronic atoms. So that means they have the same number of electrons, but they have different numbers of protons because protons give an element its identity or an ion its identity. So the trend is going to be that the size decreases as the nuclear charge increases. The nuclear charge increases because the protons are increasing. And so as the positive charge in the nucleus increases, it's going to pull the electrons in tighter. So let's look at this periodic table and this concept check question number 1. So we're going to arrange the following ions in order of increasing size. So we're talking about selenium ion, bromine ion, rubidium ion, and strontium ion. All of those ions are going to have the same electron configuration as krypton, and so they're going to have 36 electrons. That means the one with the highest charge or highest nuclear charge, which is going to be strontium, is going to be the smallest. So we're going to start with selenium. These are already actually in order of decreasing size because selenium has 36 electrons trying to be pulled in by 34 protons. Bromine's 35 protons are trying to pull in 36 electrons, and so on. Let's look at the next one. Let's erase these. Concept check 2. Which of the following has the largest radius? So we're talking about sulfur, chlorine, argon, potassium, and calcium. And those are all ions except for argon. So the largest radius, so they all have the same number of electrons. They all have 18 electrons. The largest radius is going to be the one with the fewest number of protons to pull that in, and that's going to be sulfur. All right, and we'll finish up this lesson with talking and just kind of showing a pictorial of the 3 possible types of bonds. We talked about these in the last lesson. Covalent bond is formed between identical atoms, and so that means the electron density is shared exactly the same. Polar covalent, we have one ion or one atom that's pulling the electron density closer to it, and so it's going to have a partial negative, where this side would have a partial positive. And then ionic bond is complete exchange of electrons. So you'll notice in these diagrams, the positive is represented by blue, the negative is represented by red, and so in this instance, the anion has pulled all that electron density to it. All right, well that completes lessons 8.4, 5, and 6. We will move on in this chapter and we will get to electron configuration.